So now some examples here of finding derivatives where we can see the notation. And there are going to be two examples here. The first example, I'm using Newton's notation, and I'm going to use the definition of derivative that we learned when we were doing instantaneous rates of change with that h approaching 0 in the limit. So here I want to find f prime of x, or the derivative of f, when f is x cubed. Now note, I'm not saying what x is, so I don't know the x-coordinate of my point of tangency. So if I'm drawing a sketch to help me see what's happening here, which is always a good idea, there's x cubed. I don't know the point of tangency. So I just have a generic point where the x-coordinate is x, and the y-coordinate would be my function, x cubed. And then I need a second point, so we create a second point that's h units, whoops, sorry about that. That is h units over. So I have an x-coordinate of x plus h. But then to find the y-coordinate, I plug that x plus h into my function. So the y-coordinate is x plus h cubed. And then now that I have 2 points, I can find the slope between those 2 points. So I've got the change in y over the change in x. And then if you like, you can go ahead and at this point also include, okay, not only do I need the slope between 2 points, I need to move the points infinitely close together. So that's where the limit comes in. And to move them close together, the distance between them, h, has to approach 0. So if I try to plug 0 in for h now, I get 0 in my denominator, so I'm going to work on simplifying this. So I have to still have the limit as h approaches 0 because I haven't done it yet. To multiply out x plus h cubed, I'm going to take advantage of Pascal's triangle because one of the things that Pascal's triangle does is it allows me to do binomial expansion relatively easily. So the first row is for the 0 power, first power, the second power. So this tells me the coefficients for my third power. So I've got then x cubed plus 3x squared h plus 3x to the first h squared plus 1h cubed. And then I've got minus my x cubed. And then this will all be over when I simplify the denominator, h. So now I can see the x cubes are going to cancel. And I can divide what's left in the numerator by the h in the denominator. And I've still got the limit because I haven't found the limit yet. I have 3x squared plus 3xh plus h squared. And now I can go ahead and try substitution again. Well, I'm plugging 0 in for the h. It's only going in for h, not the x's. And when I do that, I get that my limit is 3x squared. Oops. And this is my derivative, f prime of x. So what does this tell us? Well, this tells us the slope of our function x cubed at an unknown x value. But it means that I can do this with a bunch of different x values. So now I say, if x is -2, the slope, or I could write it as f prime, and now that I know x is -2, of -2 would be plug -2 in for x in this. -2 squared is 4 times 3 is 12. So if x is -2, the slope of this curve is 12. If I then wanted to say, well, what if x is positive 5? Well, if x is positive 5, I plug 5 in for x. 5 squared is 25 times 3 is 75. The slope at x equals 5 is 75. And by doing it over and over again, it allows us to do it faster so that we don't have to keep doing this limit over and over and over again for all of the different x's. So now if I go to the next example, I want to find the derivative for f of x, which is equal to 1 over x this time, at x equals 2. So I do know what x is here. And for this, I know we've done this one when we did rates of change using our difference quotient. I want to use the alternative definition for derivative just so you have a chance to see it. So again, if I sketch this, 1 over x looks like this. It has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And if this is 2, I have the point 2, 1/2. And what's different here is instead of saying I'm going to move h over, I just say, well, I'm just going to pick another point on here where I don't know what x is. I don't know how far away it is. I just know it's just some other point on the curve. So those would be the coordinates of just some other point on the curve. So now I have 2 points. I can find the slope between those 2 points. So I have the change in y over the change in x. But now to move them closer together, the limit, I just say, well, x needs to approach 2. And now I have a limit that's still finding the slope between 2 points, change in y over change in x, and move the 2 points closer together. It's just instead of saying the distance between them is going to 0, I'm just saying, no, literally the x coordinate of 1 point has to approach the 2. Well, if I try substitution, I get 0 in the denominator, so that's not going to work. So I'm going to try simplifying. So I still have the limit notation. I can't do anything with the x minus 2 on the bottom. But over here, this is one of the reasons why the alternate definition is a little bit nicer. It is easier to subtract these fractions now, because my common denominator is going to be 2x. So I multiply my first fraction of 1 over x by 2 on top and bottom. And then I have my subtraction sign. And for the second fraction, I multiply the top and bottom by x. So I now have a limit as x approaches 2. I've got a fraction divided by x minus 2. In other words, I'm dividing fractions, which means I'm multiplying by a reciprocal. And these look so close to canceling, but because they have opposite signs, I can't. However, I could factor this to be -1 times x minus 2, which means I now can cancel the x minus 2's, and I'm left with the limit as x approaches 2 of -1 over 2. And now when I simplify that, oops, I had an x disappear there. I'm so sorry. Let me fill that x back in over 2x, not -1 over 2. I accidentally dropped my x in the denominator here. I have -1 over 2x, and now when I try substitution again, I can drop the limit notation because I'm actually finding the limit. I have -1 over 4. And this is the slope of my function 1 over x at x equals 2.